Welcome everyone to this third lecture of thermodynamics. Myself Varad Daoo. I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. So in the previous class we have seen about what are internal energy, and we also studied about what are the state functions as well as what are non-state functions. Then further we also saw about what is a thermodynamic equilibrium, what are the different types of processes. For example, isothermal process, adiabatic process, reversible process, so on and so forth. Then we at the end we also studied about internal energy and change in internal energy, and we also saw that internal energy is nothing but a state function. So in today's class we are going to delve deeper into it, and then we are also going to define some path functions as well, which are like heat and work. So let us begin. So this is lecture 3, thermodynamics. So the first topic which we are going to see today is internal energy change. Internal energy change as a state function. Okay. So the absolute value of internal energy possessed by a substance cannot be calculated because it is not possible to find the accurate values of different types of energies such as translational, vibrational, rotational and chemical energy which is stored in the system. However, we are interested mostly in the change of internal energy which occurs during the chemical reaction, and the change in internal energy of a reaction may be considered as the difference between the internal energy of two states, right? So for example, we have a state A and a state B, and let's say the internal energy at state A is UA and internal energy at state B is UB. So it is impossible to calculate the absolute value of internal energy for UA UB. However, we are mostly interested in the change in internal energy, change in a quantity, internal energy, which we are going to denote as delta U, right? Therefore, change in internal energy between state A and B is given by UB minus UA, right? The difference in internal energy has a fixed value and will be independent of the part taken between two states, right? Now, why is that? Because internal energy is a state function, right? So let us write this down. The difference in internal energy delta UAB is independent of the part taken between two states A and B, between two states A and B, right? For chemical reaction, the change in the internal energy may be considered as the difference between the internal energies of the products and of reactants, right? For example, for chemical reactions, delta UAB is nothing but energy of products minus energy of reactants, right? Which is nothing but, if we use an abbreviation, UP minus UR, which is nothing but delta U. Let us drop this A and B, right? Where UP is internal energy of product, and UR is internal energy of reactants, right? And delta U gives the change in internal energy. Delta U is nothing but change in internal energy, right? If the internal energy of the product is less than the internal energy of reactants, then delta U would be negative. On the other hand, if internal energy of product is more than the internal energy of the reactant, then delta U would be positive, right? So let us write this down. If the internal energy of the products is less than the internal energy of reactant, then delta U would be negative, right? Which means delta U, which is UP minus UR, which is negative. That is, UP is less than UR, right? For example, mod of UP is less than mod of UR, right? This is the first point. The second point is On the other hand, if the internal energy of the product is more than the internal energy of the reactant, the delta U would be positive, right? Which means delta U is nothing but UP minus UR, which is positive, that is UP is greater than UR, right? Thus the internal energy U is a state function. This means that delta U depends only on the initial and final state and is independent of the path. In other words, delta U will be same even if the change is brought out differently, right? Hence, therefore, delta U depends only on initial and final states, and U is a state function. So now the second point which we are going to cover is modes of transference of energy between system and surrounding. Modes of transference of energy between system and surroundings. So every system has a definite amount of energy. It can exchange energy, which in terms of losing or gaining energy, with the surrounding in a variety of ways. Two important modes of transfer of energy between the system and the surrounding are heat and work. Right? Heat can flow into the system or heat can be flown out of the system as well. Similarly, work is either done on the system or work can be extracted from the system. Right? So let us write this down. So every system has a definite amount of energy. It can exchange energy. With the surrounding in a variety of ways. The two most important modes of transference of energy between the system and the surrounding are heat and work. So let us first understand heat, which is denoted by the symbol small q, right? So energy is exchanged between the system and the surrounding as heat if they are at a definite temperature. For example, if a system is at a higher temperature than the surrounding, then energy, that is nothing but heat, is lost to the surrounding, causing a fall in temperature of the system and rise in temperature of the surrounding. This process continues till the temperatures of both system and surrounding become equal. If the temperature of system is lower than the temperature of surrounding, then the energy is gained by the system. In other words, we say that there is a flow of heat from system to surroundings if system has higher temperature, and there is flow of heat from surroundings to the system if the former is at higher temperature. This exchange of energy, which is a result of temperature difference, is called as heat. For example, suppose we take water at temperature TA in a container having thermally conducting walls, say made up of copper, and enclose it in a huge heat reservoir at temperature TB. The system will absorb heat from the reservoir, and this heat absorbed by the system can be measured in terms of temperature difference, which is TB minus TA, and in this case the change in internal energy will be nothing but equal to heat transfer when no work is done at constant volume. Right? So let us write this down. Energy is exchanged between the system. Energy is exchanged between the system and the surrounding. Between the system and the surroundings as heat if they are at different temperatures. For example, if system is at higher temperature than the surrounding, then energy or heat is lost to the surrounding, causing a fall in temperature of the system and rise in temperature of the surroundings. Right? This process continues till the temperature of the system and the surroundings become equal. If the temperature of the system is lower, if the temperature of the system is lower than that of surroundings, then energy is gained by the system. In other words, we say that there is flow of heat from system to surrounding. We say that there is flow of heat from system to surroundings, if the system has higher temperature, and there is flow of heat from surroundings to the system, if the former is at higher temperature, and this exchange of energy, which is a result of temperature difference, is called as heat and is denoted by symbol Q. So in order to understand in depth, let us drag a picture. For example, from this picture we see this is an exchange of heat between system and surrounding when the temperature of the system decreases, right? So we have a system which is hotter than the surrounding. Then for example, let's say its temperature is T1 and the temperature of the surrounding is T2. Now what we have is T1 greater than T2, right? That means heat is going to flow outward, right? Like this heat is going to flow, and because of this T2 is going to increase to T2 dash, and T1 is going to decrease to T1 dash, and this is going to continue till T2 dash becomes approximately or exactly equal to T1 dash, right? The second image is this one, in which we have exchange of heat between system and surrounding where the temperature of the system increases, right? So in this case, the exactly reverse thing is going to happen. Let us consider the system is at temperature T1 and surrounding is at temperature T2, and we have T2 greater than T1. Now as time progresses, T2 is going to change to T2 dash and T1 is going to change to T1 dash. But because T2 is greater than T1, what we are going to observe is heat is going to flow into the system from all directions uniformly, right? And this is going to continue till T2 dash becomes equal to T1 dash, right? Okay. And this exchange of heat, this exchange of energy in the form of in this form is called as heat, right? So some important points which has to be noted is Q or heat is positive when heat is transferred from the surrounding to the system, and so point 2 is Q is negative when heat is transferred from the system to the surroundings, right? So let us now understand about thermodynamic scale of temperature. Okay, so thermodynamic, which we have also studied, which you might also know as Kelvin scale, thermodynamics scale of temperature. So in our daily life, we come across various objects having different degrees of hotness or coldness according to our physical sense. Temperature is a measure of degree of hotness or coldness of a body. To understand the hotness or coldness, we need a recognizable temperature scale and make all measurements of hotness with reference to it. On the Celsius scale, the reference points are ice point, which is at 0 degree centigrade, and the steam point, which is at 100 degree centigrade. And the scale is divided into 100 equal parts, each parts representing 1 degree centigrade. The Kelvin scale has been universally accepted since 1954 by the International Committee on Weights and Measure. In this scale, the absolute zero of the temperature and the triple point of water. Now what is triple point? Triple point is a temperature at which all phases of water, that is ice, liquid and vapor, coexist, are in equilibrium. So triple point of water corresponds to a fixed temperature and pressure of 0.01 degree centigrade and 4.5 at torr. The basic SI unit of temperature is Kelvin, and 1 Kelvin is defined as 1 by 273.16 of the triple point temperature of water. Okay, so let us write this down. So 1 Kelvin is nothing but 1 by 273.16 of the triple point temperature of water, which is 273.16 Kelvin. The scale is mostly used in thermodynamics and is called as thermodynamic temperature scale, right? And this scale is called as Kelvin scale, is also called as thermodynamic temperature scale, right? It is also called as absolute scale. This is also called as absolute scale. Now why is it there? Because on this scale the lowest possible temperature has been taken as 0, unlike Celsius case in which 0 point has been taken arbitrarily. Now the second terminology which we are going to study is work. We are going to study work and is denoted by symbol W. So it is another mode of work is another mode of transfer of energy. Work is said to be performed if the point of application of force is displaced in the direction of force. It is equal to the force multiplied by the distance, which is nothing but displacement. If F is the force and dl is the displacement of the point of application of force in the direction in which force acts, then work done is given by W, which is nothing but F product of F and dl. So there are two main types of work which we generally come across. These are electrical work and mechanical work. So electrical work is important in system where reaction takes place between ions, whereas mechanical work is performed when system changes its volume in the presence of external pressure. Mechanical work is more important, especially in system that contain gases, and this is also known as pressure volume work. Right? So let us write this down, that work is another mode of transfer of energy. Work is another mode of transfer of energy. Work is said to be performed if the point of application of force is displaced in the direction of the force, right? It is equal to the force multiplied by the displacement, right? Now if F is the force, if F is the force and dl is the displacement, if F is the force and dl is the displacement of the point of application in the direction in which force acts, then work is given by W is nothing but product of F into dl. So there are two main types of works which generally arises. So work usually are of two types. These are electric work and mechanical work, which is also called as pressure volume work. So we are mostly going to deal with this mechanical type of work. Okay. So in order to study this, let us understand this with the help of a picture. So let us see this image and let us examine a change in internal energy by doing work. So let us consider a system containing some quantity of water in a thermoflask or in a insulated beaker. So this would not allow the transfer of heat between the system and the surrounding through its bonding. So transfer of heat is equal to 0, that means delta Q is equal to 0. We call this type of system as an adiabatic system, right? Adiabatic system. Okay. The manner in which the state of the system may be defined will be changed will be called as an adiabatic process, right? So the process in which system changes its state is nothing but adiabatic process, and we know that in what is an adiabatic process? So adiabatic process is the process in which there is no change of there is no interaction of the system with the surrounding in terms of heat, right? Because there is no transfer of heat between the system and the surrounding. So in this system, the boundary wall which separates the system and the surrounding is called as an adiabatic wall. So this wall is going to be adiabatic wall, and it's an insulated beaker. Okay. So let us bring the change in the internal energy by doing some work on the system. Okay. Let the initial state of the system to be state A and its temperature be TA. Let the internal energy of the system in state A be UA. Now we can change the state of the system in two different ways, right? So let us first write this down. Let us bring the change in internal energy, by doing some work on the system. So let the initial state of the system be state A and its temperature PTA. Let the internal energy of the system in state A to be UA. Now we can change the state of the system. In two ways. So first way is one way of first way, right? Suppose we do some mathematical or mechanical work. Okay, say 1 kilogram, so 1 kilojoule of work by rotating small pedals and thereby churning the water. This will convert all the mechanical energy of the rotating pedal into heat energy by friction between pedals and water. Yes. This heat will result in the rise of temperature. Let the next state be called state B. And its temperature be TB, whereas TA is less than. Let the internal energy of the system in state B be UB, and change the internal energy, and then the change in internal energy is going to be delta U, which is nothing but UB minus UA, right? The another way or second way is going to be the second way is going to be, suppose we do an equal amount of work. Number one, suppose we do an equal amount of electric work, which is 1 kilojoule. We heat the water with the help of immersion rod, and it will be observed that change in temperature is same as in earlier case, which is TB minus TA. In fact, Joule performed a series of experiments. During the year 1840 to 1850 to find the relationship between mechanical work and heat produced. By performing careful experiments, Joule found that a given amount of work done on the system, no matter how it has been done, irrespective of the path, always produced the same change in state as measured by change in the temperature of the system. For example, irrespective of the method used for converting mechanical energy to heat, every time for 4.186 kilojoule of mechanical work, exactly same amount of heat has been produced, which could raise the temperature of 1 kilogram of water by 1 kg 1 kilogram of water by 1 degree centigrade, right? So let us write this down. So second way, so suppose we do an equal amount of electric work, which is 1 kilojoule. We heat the water with the help of immersion rod. It will be observed that change in temperature is same. As in earlier case, that is Tv minus Ta. Right? Thus we observe that the value of internal energy is characteristic of the state of the system, and the adiabatic process, that is work done required to bring about a change, is equal to the difference between the value of U in one state and that in another state. Okay? Thus we observe that the value of internal energy is characteristic of the state of a system, and the adiabatic process work, which is work WAD, required to bring about a change is equal to the difference between the value of U in one state and that another state, that is delta U. So delta U is going to be nothing but U final minus U initial. Okay, so thus we can say, internal energy, which is U of the system, is a state function. The positive sign expresses that work of adiabatic is positive when work is done on the system. Similarly, if work is done by the system, then work of adiabatic is negative. So in this class, what we have seen about internal energy, and we have also studied about two different forms of ways, modes of transfer of energy between system and surrounding. These are heat and work. So in the next class, we are going to study about pressure volume work and the expression for calculating this work in terms of reversible as well as irreversible processes. So I stop with this, and I thank you all for attending this class, and I hope to see you all again in the next class. Thank you.